going to start talking a little bit about applications of first order ODEs. And our favorite application of ODEs is, of course, growth and decay, because in no way have we been doing problems like this pretty much constantly since we were like 8 years old. There's always like, there's blah, 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 and the half-life is blah, blah, blah. So how much is there after blah, blah, blah time? Well, that's an application of a first order ODE. So we're going to solve the same problems you've been solving for a while, except we're going to solve it more like sophisticatedly, like with our nose in the air, like general academic snubbery. Like, I know you think that you've been solving it, but we're going to solve it using DiffyQ, because that means we're way smarter. So there. So we're going to do a little bit of a derivation, we're going to do an example, and then we're going to do something really important. So don't stop the video at the end, or until the end, because we're going to do something that's kind of important as you go forward. All right. So when we talk about exponential growth and decay, we define something along the lines saying the rate of change of the quantity Q. So quantity. So basically, instead of doing everything's in y's and x's, we're going to be using q's and t's. So no y's and x's now, everything's going to be in q's and t's. So we have the rate of change of some quantity Q is proportional to Q. So in math speak, we know that when we talk about rate of change, then that means ddq, or ddt. And then is of course a question mark, so the rate of change of quantity Q is proportional to Q. And by proportional, that usually means that we're going to multiply by some constant and then Q. So the rate of change is proportional to that quantity itself. Now, the way that we work is if A is greater than 0, we call that growth, which makes sense because the change would be positive. If A is less than 0, we call that decay, which again would make sense because the rate of change would be negative. So because we know how to do DiffyQ now, we can actually solve this, which is kind of exciting. So I've got all my Q's on one side, and I've got everything else on the other side. So I'm going to integrate both sides of this equation somehow with like a integration thingy. Integrate on the left. Well, or I could just use the fact that I know the answer to this. I know that the answer to this in general is going to be Q is equal to C e to the, well, negative because it'd be on the other side, really positive A dt. But we're going to go ahead and work that out anyway, just in case you don't remember that. Natural log of Q is equal to AT plus C. So that means Q is equal to e to the AT plus C, but we don't really need the plus C there, so we can say Q is equal to C e to the AT. Beautiful? Now, on these we usually have some initial condition. So say we have an initial condition that says that at time equals 0, the quantity of Q is some Q naught. You're like, wow, that's really not that exciting. The only reason it's exciting is because we say Q naught would be, so Q at 0, Q naught, which would be Q, is equal to C e to the A times 0, which is just C times 1. So that means C is equal to Q naught. The reason we care is that allows us to rewrite our equation as Q is equal to the initial value times e to the AT. Now, we're saying e to the AT. It's important to note that T really is T minus T naught. We're just always assume that T naught is equal to 0 because we always have, I guess. This isn't a big deal until you get to applications like circuits where you have switches that are flipping at different times. So if you have a switch that flips at time 0 and then another switch that flips at time 3, then this kind of stuff, because you see the stuff like this in circuits, would look like this. So we're going to ignore that. I'm just kind of warning you that if you're like, how come my book says T minus T0 and hers doesn't? Because I'm assuming T0 is actually 0. So there you go. We've got ourselves a nice little equation to get started. Fantastic. Okay, so let's do a perfect, lovely little example. And like I said, after the example, I'm going to do something else that's kind of algebra heavy, so hold on to the end of the video to make sure that you get a chance to see that. So if you already know how to do these problems, just go ahead and skip ahead a little bit so that you know that last little topic. So say we have a radioactive substance, radioactive thing, substance, has a half-life of 1620 years. Okay, so we'll say something like, we'll have two questions. If the mass is 4 grams, how much will be left in 810 years? right? So in half as many years. And then also find the time t 1.5 grams remains. All right. Now, before we can even solve this problem, we have to start out with coming up with an actual equation, because remember our equation says Q is equal to Q naught times e to the AT. Now, for the problem that we're looking at, we know the initial amount, and we know what the half-life is, but there's nothing in this equation that has like H for half-life, okay? So the half-life is not just T, like, well, it kind of is, but you got to think about it. So there's a couple ways to do this. Basically, we need to, our first step is to find A. All right, so our first step is to find the radioactive constant, or the decay constant. All right, so kind of a straightforward way to do this, in a way you would do this if you were in, say, a college algebra class, is you're going to pretend that we have 1,000 grams, and in one half-life, how many will we have left? We'll have 500 grams. So that's in 16 and 20 years. 16, 20 years. All right, so we can put that together in our equation. So the current amount that we have after one half-life would be 500 grams. Our initial value was 1,000 grams, and that's going to be equal to e to the a times the time that has elapsed, which is 1620. Now, the only reason I picked 1,000 and 500, you could pick 150, or you could pick 1 and 1/2. The only reason I care is it gives me a half here on the left, equals 1620 times a. Okay, but remember, I'm trying to solve for a, so I have natural log of 1/2 equals 1620 times a. This is going to be kind of an ugly little thing, but you know, it's okay. So I have that a is equal to natural log of 1/2 divided by 1620. If you want to simplify that a little bit without a calculator, you have natural log to the negative, or 2 to the negative 1, 1620, which means I can pull the negative out front. Negative natural log of 2 times 1620, which is, you know, it was okay. So that's a. We care about a because that means we can put together our actual equation. Our actual equation is Q. The current value is equal to the initial value times e to the AT. Now we know that a is natural log of 2 over 1620. So this is our guiding equation, I guess, that covers everything that we've got. So that's kind of fun. Guiding equation. Okay, so now what we want to do is we actually want to solve the problem, and I already forgot what that was because I got so excited about the math. All right, if the mass is 4 grams, how much will be left in 810 years? So if our current mass, so pause the video, see if you can put this together. This really shouldn't be too much of a stretch. So if the current mass, or the initial mass, is, what do we say, 4 grams? So that means our initial is 4 grams, natural log of 2 to over 1620. How much is going to be left in 810 years? There we go. All right, so, and we can pretty much do this by hand if we want. So that's natural log of 2 over 2. So that's 4 times e to the negative 1/2 natural log of 2. And I could do this on a calculator. I'm just doing this to show you how amazingly fantastic I am at, you know, log rules. All right, so that means it's 4 times 2 to the negative 1/2. And now this is really just super duper for funsies. 4 over the square root of 2. Mama said never take a square root in the denominator when you go to a party. So 4 root 2 over 2, 2 root 2. So basically, in 810 years, I'll have 2 times the square root of 2 grams, which kind of makes sense. I'll have a little bit more than half of it left. So that makes sense. That's kind of nice. This is really just a reminder. You probably have worked problems like this before. It's just a question of, you know, of just remembering the derivation, really, I guess. All right, so then it was find the time t when 1.5 grams remains. So we can do that. So if we start with 4, we're going to end up with 1.5. That's e to the negative natural log of 2 over 1620 times t. At some point, I'm probably just going to break down and use a calculator, but I only marginally care about the actual answer. I just care to make sure I actually know how to solve it. Let me take what's 1.5 over 4? It's like 1.5 or 15 over 40 divided by 8 is, or divide by 5 is 8. Well, not 8 on the top, divide by 5 is 3 eighths. Take the natural log of both sides. What is she doing? I've got the natural log of 3 eighths is equal to this thing. This is not really that impressive, but this would look a whole lot better with a actual number, but yeah, that's all I really got. I could switch this 8/3 and get rid of the negative sign, but I can't combine those natural logs just because I can't. I could get out a calculator and solve this if I really cared, but if not, I have a perfect solution. This is the exact solution that in that long, however that long is, I will have exactly 1.5 left. Now, in case you are just trying to fast forward, seeing to the part that I said you really, really want to see this is the part that you really, really want to see, so I'll draw a big giant flower. So the part that you really, really want to see. All right, so we're going to do the same thing, but we're going to say that it has a decay k. And we want to, how do I want to say this? Basically, the idea is that we can increase and, hold on, let me think this through. Hold on just a sec. Okay, so let's be a little bit more interesting about this. So we'll say that, like I was going to say, we have a radioactive substance with decay k, but we're going to say it's also produced at a rate of A units per time, or units per unit time. So how do we describe this? So what if it's decaying, but it's also being produced? Okay, so does that make sense? So it's being produced as well as decaying. So that's kind of what I wanted to start getting you guys thinking about. So the idea is we have this change. So it's changing in the fact that it's decaying, and we'll just say it's negative because it's less than, we said if it was less than 0. So it's decaying at a certain amount, but it's also increasing at a constant rate. So the idea is this with these decaying problems, that in addition to having some kind of half-life or decay or something like that, you can also have some growth. So this would represent the decay, and this is going to represent the growth. Okay? Kind of seeing how this is working, maybe a little bit? Okay, so we can solve this problem as well, of course. I can get all the k's or q's on one side and all the t's on the other, and then integrate. Now, whenever I integrate on the left, I get the natural log of a to the minus q over k, except if I differentiate that, I'm going to get an extra negative sign, so there's a negative sign there, and then this is some random t plus c, like that. What else can I do? I'm going to, not just a minus sign, to be a minus sign with 1 over k. Yes, okay. I thought that looked a little bit funny. Okay, so if I put this over here, I can say the natural log of a to the minus kq to the negative 1 over k is equal to t plus c. Let's see. And then I can fix that to say that a to the minus kq to the negative 1 over t is equal to e to the t plus c, or I can, instead of saying e to the t plus c, I can just say some other constant, e to the t, like that. Beautiful? Okay, so if I raise both sides to the negative k power, then that gets rid of that stupid thing on the left, and I've got c, again, it's, it's good. E to the negative kt, like that. Now, why am I doing all this? Trust me, there's a reason. Eventually, we'll get there. I'm going to go ahead and I'm going to solve for Q. So Q is going to equal A over K minus, and I'm just going to fix this up a little bit here, K times C to the K times E to the KT, like that. So I've got this lovely little equation for Q. Now, again, we're going to come in here and we're going to say that at time equals 0, Q is equal to Q naught. So at time equals 0, Q is equal to Q naught, which is A over K minus 1 over K C to the K E to the 0. So Q naught A over K minus 1 over K C to the K. And I can mess around with that a little bit more, and I can solve that 1 over C to the K is equal to A minus Q naught K. Well, just by multiplying everything through by K and then moving this stuff around, so hopefully you can get there. All right, and the reason we care is now we can plug that into our original equation, A over K minus 1 over C to the K. You're like, this is really stupid. How much longer do we have to do this? You have to do it forever. Actually, you don't have to do anything. You're watching a video about DiffyQ probably at 2 in the morning because you just desperately want to know more about it. So I've plugged that in there. I've got the E to the KT back. So now this is my beautiful equation that absolutely describes everything. Why do I care? I don't know why you care. Just something that you do. You can't help yourself. Okay, next step. I boxed in the wrong one. I got excited. What I really meant to say is we're going to take this here and we're obviously going to plug it into here. So here we go. Bump da 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 da. I like to do math in my free time. Kind of. Ba 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 ba. Okay, I'm going to pull the K out just because, you know, it looks like a good idea. A over K. Divide the whole thing through by K. I'm actually going to switch the order of these as well. So the Q is going to go first, and then minus A over K, and then 1 over E to the KT. And I'll just go ahead and put that on top like this. All right. Why did I go through all this problem? Okay, this is kind of weird, but you're going to get it. It's going to be amazing. Kind of amazing-ish. Ish amazing? Okay. The reason that we like this equation is it's in a specific form, and this is a form you're going to see throughout differential equations, not just in first order ODEs, but also in second order ODEs. Now, if you notice right here, this is the initial condition, okay? Now, whenever we do DiffyQ, a lot of times we can rewrite our solution in this exact format. Now, I want you to see what happens if I take the limit as t approaches infinity. So obviously it doesn't affect the first term. Now, if it go to the second term, and I'm going to write this really stupid. So we know that e to the minus kt is just the same thing as this. So if I say e to the infinity, for lack of a better word, e to the infinity is infinity. And 1 over infinity goes to 0, right? So basically that means that the limit as t approaches infinity is ak. So if you ask, well, what is the thing that happens to this equation like in an infinite amount of time, you'll notice that it doesn't do anything weird. It actually levels out. So there's all this noise, all this stuff that happens as t starts in at 0, but as it goes along, it ends up kind of settling out, and we call this settling out. We call this the steady state. And just to prove to you that this equation works, look at it at t equals 0. At t equals 0, we get a over k plus q naught minus a over k times e to the 0, which is just 1. And if you see the a over k minus a over k, you do get q naught. So that's your initial condition. So here back in your initial-ish equation, or final whatever equation, we see the steady state here. And within this response here, we see a steady state as well. So this thing right here, I'm going to move this down so you can see what's going on. No, not like that. I want the whole thing. There we go. This thing right here, we call that whole thing the transient response. So transient means obviously it's not permanent. So basically what we have here is we have this equation where we have the steady state, and then we have the transient response times e to the negative kt. So you're going to see this a lot. You're going to see this in circuits. You're going to see this in a lot of growth and decay, is that after a certain amount of time, as t goes to infinity, you're going to see a leveling out, which makes sense. You see it with population growth. If it adds at a certain rate and it decreases at a certain rate, at some point population levels out. You got this steady state. So it's really kind of cool because this is the first time you really have the sophistication to look at an equation and go, okay, I can kind of tell long term what's going on. And it's just really neat that you get within this transient response this kind of standard looking thing where you have the initial condition minus the steady state. So this is something you're going to see a lot. I really wanted you to see it so that you could start keeping an eye out for it because, like I said, it's going to keep coming up over and over again. But this is the first time we can really get into this. So this is kind of what differentiates the standard, like, oh, I did this in college algebra versus, oh, this is a legit growth and decay kind of investigation.